Hello everyone, my name is Valerie Miller and I am the Outreach Coordinator for Future Energy Systems, or FES. FES is a research program at the University of Alberta focused on studying the energy transition. When I say energy transition, you might think first of renewable technologies. However, oil and gas have an important role to play in the energy transition. Thanks so much for joining us for Let's Understand Oil and Gas. In this series of clips, you'll meet 4 researchers working in oil and gas, finding ways to reduce its impact and better understand it. In this first part, you'll meet Elena Andrianova, who will start by explaining the basics of oil and then share her research developing models to test different oil production techniques.
Hello everyone who is interested in the future energy. This is not a secret that we need oil and gas to produce energy. Thanks for oil, we can not only run our cars and heat our houses, but also we use oil to pave roads, produce electricity, and produce drugs, clothes, medical equipment, toys, and many other good things. My name is Elena Andrianova, and I am a PhD student at the University of Alberta. I am here to talk about oil. What is oil? Millions of years ago, the world's oceans were filled with plants and plankton. When this creature died, they fell to the bottom of the seas. Over millions of years, these remains were buried under their layers of sand and mud. Heat and pressure turned these remains into oil and natural gas. Oil is trapped under the ground in sand formation. Can you imagine the sponge filled with water? This is almost the same thing, but the sponge is sand filled with oil, buried under many layers of rock. Oil can be found all over the world, including North Sea, Russia, Saudi Arabia, the United States, Iran, Iraq, China, and of course Canada. Canadian engineers are spending days and nights trying to find the most environmentally friendly methods of oil production. And even though we are the world leaders in producing of clean oil, we still try to find the best ways of production. One of the big challenges in oil production in Canada is that our oil is mostly crude oil and bitumen, which is so dense that cannot flow without our help. Imagine honey. There are lots of different types. We have liquid and solid types. The liquid honey can easily flow out of jar if we turn it over. But if we leave the honey in the refrigerator for an hour, it becomes thicker and cannot flow anymore. So how we can help it to flow? We can heat it so that it becomes liquid again, or we can add some water to dissolve it. The same happens with heavy oil. We have 2 options: to heat it, that are what steam-assisted gravity drainage or SAGD and cyclic steam injection technology is about. Or we can dissolve it by using solvents. That is what WAPEX is about. Solvents are basically light oil or gas that can dissolve into bitumen, reducing the viscosity or the thickness. The same as acetone applied to nail polish. These are main methods of bitumen production. However, unfortunately, they have some drawbacks. The heating-based technologies inject hot steam under the ground, so a lot of water and energy are required, making the process not so environmentally friendly as it could be. Solvents-based methods are more ecological because they require less energy and water, but they work slowly, and so they are less profitable. The solution could be the combination of these 2 technologies, so a combination of heat and solvent. These methods are very promising and showed good results in recent years. However, we cannot just start using the methods without testing, because it can be unsafe for the environment or couldn't work at all. The same as with vaccine, we cannot test it on humans without testing and doing a lot of experiments. how we can study the method. That is what my research about. We can do tests or simulations. The easiest way to predict the future is to make a modeling or simulation, when we can make a computerized copy of oil reservoir and test any desired production technique on it. If the model is small and simple, the simulation is just seconds. But thermal solvent associated technologies are quite complicated, and it can take days and weeks to run a single model. This makes it hard to test lots of different production methods. So the aim of my research is, and the, so the aim of my research of my team is to develop model that works faster under these complex conditions. One of the challenges of faster model is that they may be less correct. Imagine we are doing a really hard math problem on a test. If you do it very fast, you might be wrong. But if you answer very slowly, you may be correct, but you may not have time to finish the rest of the test. The methods we are working to create should be able to make models work faster, but also remain accurate or correct. By making it easier and faster to test the oil production processes, we can improve technologies so that we can produce oil more environmentally friendly without losing money and economical efficiency. Thank you so much for your attention. If you have any questions, feel free to contact me and the Future Energy System team. We will be happy to hear from you.
Hello, my name is Juliana Leung, and I am an associate professor in engineering. A young community member asked, what happens when an oil well runs out of oil? Well, interestingly, when an oil well runs out of oil, it doesn't mean that we have taken out every drop of oil from underground. There's a lot of oil stuck in different parts of the rock. It's like drinking from a juice box. There's always a little bit that's stuck at the bottom, no matter how hard we try to get it out. And for an oil well, we often leave behind more than just a few drops. But getting more of that out would take way too much energy. So at the end, it's not really worth it. Sometimes we might drill another well in the area to continue producing. But when we finally decided that a well is done, we can't just leave it behind because things might leak into the environment. We must close it off properly. So engineers will plug it, disconnect it from other facilities and pipelines, and make sure that things are safe. I hope you have enjoyed my answers, and thank you very much for your question.
In this next part, meet Basuk Bagliani, who is researching wireless sensor technology to improve monitoring for steam-assisted gravity drainage operations.
My name is Basuk Bagliani, and I'm a postdoc fellow with the University of Alberta, and I'm presenting wireless sensor technology for heavy oil applications. So the main method for extraction of bitumen as the heavy oil is the steam-assisted gravity drainage called SAGD. And for SAGD, they have two horizontal pipes in the well. They have very long, and they put in top of each other, and the top one, they inject very hot steam through the top one, and they extract the bitumen from the bottom one. Because bitumen is very, very viscose, it's not easily extractable using like the conventional oil. So they needed to increase the temperature of the environment. So that's the reason they inject very hot steam at the top pipe. At the bottom pipe, they have water, because they injected the steam before. They have bitumen and clay. So these are the three materials that are extracted through the bottom pipeline. But this requires a very large amount of water, and it's very high energy intensive process and require high gas emission rates. So altogether required a demand for real-time monitoring of the process during the extraction. So, for example, just considering the required amount of water for this process, we could uh, use this data from Oil Sand Magazine in 2018. Let's compare the irrigation agriculture water consumption in Alberta is just 44%, while the oil sand itself is 8% of the whole water consumption. It's about the municipal water consumption is 11%, so the oil sand is comparable with the whole municipal water consumption. After production and refinery processes of bitumen, it should be transported mostly through pipelines. But pipelines are unfortunately have a big problems of breach through the pipelines or spills because of loose fittings or not appropriate endings and etc. And it's cost about $18.7 billion annually. And that's another problems that we're going to address by monitoring the pipelines in a real-time fashion to be able to detect any breach during the process. So we developed the sensors, the microwave sensors that are able to monitor the water breach as well as measure the concentration of water, clay, and bitumen in downhole. These sensors are copper traces formed as split rings, and they're extremely low cost. They're very high sensitive because when you put the material on top of them, they're able to detect the variation of that material because each material has its own dielectric constant. And also it's non-contact. This structure is comprised of a very simple tag, which as said, it's a very thin sheet of copper, and it's electromagnetically coupled with a reader. So the reader doesn't need to have any contact with the material under the test. And so the structure is non-contact and non-intrusive, and it's able to work in harsh environmental conditions, just a simple metal layer without any electronic device. It doesn't require a battery because the coupling is electromagnetic. And it's also an ideal for Internet of Things applications, which we can hear about all over the place. So these are two samples of our experiments. The one in the left was the sensing mechanism for bitumen monitoring that we have done at a very high temperature of 210 degrees C under turbulence, and we're able to monitor the bitumen and water concentration at that high temperature using this sensing mechanism. And for the right one, we were able to determine the water contamination in biofuels with multiple variable mixture using artificial neural networks and the developed microwave sensor. All the works that we were doing in the lab is that are dedicated to the memory of Professor Mushgan Danishmand, who passed along with her family in January 2020 in the Ukrainian International Airline Flight 752 tragedy in Tehran. My special thanks goes to my colleagues in M2M Lab, especially Zahra Abbasi and Nabi Hussein.
A community member has asked about shale gas and how is it different from oil sand. So first of all, what is shale gas? It is a form of natural gas resources found in shale formations. Shale is a fine-grained sedimentary rock with extremely low permeability, meaning that it has tiny pores that are poorly connected. So it is very difficult for anything to flow in it. In the past, this type of resources would have been very difficult to develop. But in recent years, because of the advances in technology and increasing energy demands, commercial development of shale gas resources is very common now. How is it different from oil sand? Well, I can come up with three main differences. The first one is that shale reservoirs are located at much greater depths, usually several kilometers. Oil sand or bitumen reservoirs is located at shallower depths, usually a few hundred meters. Resources that are buried at a depth less than 75 meters can be recovered from surface mining generally, but only approximately 20% of the resource is mineable. So the remaining 80% has to be recovered using in situ techniques by drilling wells. The second difference is that oil sand reservoirs usually consist of big pores. So they're very permeable, but the challenge is that the bitumen is very heavy. It has high density, very viscous, so generally it doesn't flow very easily into the wellbore. That led to the third difference, which is the extraction technique. Now, in both settings, we use horizontal drilling, but for oil sand, hot water, heat, steam, chemicals are often added to help to make the bitumen less viscous. And special consideration is also needed when transporting bitumen in pipelines, as diluent is usually added to dilute the bitumen. For shale gas, the challenge is to make the rock more permeable. So this can be achieved using a technique called hydraulic fracturing, where we inject water at high pressure to create cracks in the rocks so that the gas can flow into the cracks and then from the cracks into the wellbore. I hope I've answered your questions, and thank you very much for your interest.
In this final part, Erin Valerie will explore the use of model emulsions to improve oil production and reduce its cost and environmental impacts.
Hi, my name is Aryan Velayati, and I am a PhD candidate of petroleum engineering at the University of Alberta. And thank you for watching this short presentation on our research. Today I'm going to talk a little bit about the emulsions and the role of emulsions in the petroleum industry and how we are conducting experiments and doing research in the lab on that specific topic. Like any other engineering work, the final goals of this research is to improve the efficiency and lowering the energy that is used in the industrial operation. In this case, production from hydrocarbon resources. In a highly efficient system, the costs are reduced and the environmental impacts like CO2 emission is reduced as well. But such study is not possible without having a reliable model that represents the actual physical phenomenon that is happening. In our case, we are looking into emulsions. But what is an emulsion? Milk, cream, ointments, these are all emulsion products. Emulsions are widely used in many industries, including the pharmaceutical industry, the food industry, and of course, the petroleum industry. But let's get into more details about the nature of emulsions. Emulsion is a system of liquids that are not quite soluble in each other. One phase is then dispersed in form of droplets in another phase, which is the continuous phase, and it contains the droplets. In case of milk, the droplets are the fat liquids, or liquid fats actually, and the continuous phase is the water. So you have an oil in water emulsion. But the thing is, the phases and the liquids in this emulsion tend to separate very fast. And that is why we use emulsifiers and surfactants in the system. These surfactants cover the droplets and change the molecular forces in a way that the phase separation in the emulsion is delayed. As I've mentioned before, emulsions are also produced in the production of oil. It could happen anywhere. Formation of emulsion can happen inside the reservoir, which is the formation from which you produce hydrocarbons, or inside the well or the downstream. But the most dominant type of the emulsion that you get in this industry is a water in oil emulsion. Is it wanted or unwanted? It is absolutely unwanted from a production engineering perspective because the way this type of emulsion flows is very different from its constituent phases. It is more thick, it flows harder, especially in case of a water in oil emulsion. That is why we are interested into looking into behavior of this emulsion in different conditions. So we are trying to build a model in the lab, a model emulsion. A model is a representation of an actual physical phenomenon. with features similar to that of the actual physical phenomenon. In this case, we're trying to have emulsions that are similar to the main properties of the emulsion that is formed inside the reservoir. It is not easy to have access to the bitumen from the reservoir. And even if you have access, there's always the risk of fire and explosion and the safety risks. So we are using green emulsifiers and we are using other components to have a reliable model. And this model emulsion should mimic some specific properties of the actual emulsion that is formed inside the reservoir, including the droplet size and droplet size distribution, and more complicated ones, such as the viscosity or how it flows, and the stability of the emulsions. Thank you very much for watching this short presentation. And if you are interested to know more about this research, please check out the FES website.
Thank you so much for joining us to better understand oil and gas. Make sure to subscribe to Future Energy Systems YouTube channel so you don't miss any of our exciting content, and check out the links below. There's so much to learn as we explore our energy future.